Hi everyone. In this video lesson, we're going to analyze some collisions in two dimensions because momentum is conserved and momentum is a vector. That means that that momentum is not only conserved in one dimension, but when we have two dimensions, momentum is conserved both in our x direction and our y direction. And we're going to use that to solve some collision problems. So what my plan is for this lesson is we're going to solve two problems with where I basically give you guys a step-by-step walkthrough where I believe you at home could actually just do the problem following those scaffolded steps. I'm going to go through the walkthrough with you, and then we will look at a problem and we'll solve without a walkthrough where we just apply a little bit of the methods we've learned in our first two examples and maybe some older methods we've used as well. In this lesson, we're just going to analyze three collisions in two dimensions. So let's get started. So as you can see here, in this two-dimensional collision, we have a dump truck moving east with a speed of 15 meters per second and a car traveling north at 32 meters per second. So they collide at the middle of the intersection. And then they, in this question, we've said they become entangled. So this is a purely inelastic collision. So they're going to couple together and move together in the same direction at the same speed. And what we would like to do is we'd like to analyze what that speed and direction is. So here's how we're going to approach this one. As I said, got a little bit of a walkthrough for us to do. So we're going to, in this problem, let east and north be positive. So when we analyze things in the x direction, we'll use positive for east, negative for west. In the north-south, positive for north, negative for south. And in this resource, I've got capital P in here. So I understand we've been using lowercase p, but you guys will be fine. We'll just pretend that it's a lowercase p for now. So if we say that the truck is our mass 1, and our car is mass 2, well, what's the momentum of the truck in the x direction? Well, it's moving purely east, right? So we don't need to do any components or anything. It's just speed, 15, times its mass, 300. I think I said 300. 3,000 for its mass. Remember, momentum is just mass times speed. So 3,000 times 15. So 45,000 kilogram meters per second, and that's going to the east. Now, our second car is traveling north. Does it have any momentum in the x direction? No, the answer is no. And so the momentum for this guy is just 0. So it's helpful when things are 0. And in the same way, the truck, who is moving purely to the east, has no component of momentum in the up, down, north, south direction on our page. Its momentum is all north, south, and its mass is 800 kilograms. And we said it was moving with a speed of 32 meters per second. So 800 times 32, 25,600. All right, so momentum is conserved. In two dimensions, momentum is conserved in the x direction and the y direction. So the total initial momentum in this scenario, in the x direction, from both cars, it's just 45,000 kilogram meters per second east. And because it's only one car contributing to the total momentum there. And same in the y direction, the total momentum in the y direction is 25,000 kilogram meters per second. Now, we didn't need to have cars traveling at a right angle. Both of those cars could have been traveling at an angle. And in that case, we would just find the component of momentum in each one for the x direction and add them up. So the total x momentum, 45,000 kilogram meters per second. The total y momentum, 25,600, and that's north. That's north. So based on the law of conservational momentum, what are the values of the x and y momentum after the collision? Well, momentum is conserved. So if the total momentum in the x direction was 45,000 before the collision, that's the momentum after the collision. And the same thing, the momentum in the y direction before the collision is the same as afterwards. So we don't need to do any work for that. That's just conservation of momentum. But if we know the x component of momentum and the y component of momentum, we can combine those two vectors to get the total momentum, some vector at a diagonal to, or at an angle to east and north. And if we know that momentum and we know the combined masses, we should be able to find the speed. So I prompted you guys to do that. So the two cars become entangled. So again, we're going to assume that the velocities of the two cars are the same. And we're going to use Pythagorean theorem to find the resultant momentum after the collision. So we have 25,600 units of momentum going up, kilogram meters per second. And to the right, we had 45,000. We're going to combine those to get the total final momentum. I'm going to call that P, a little subscript T for total, and F for final. And we can find that magnitude pretty easily. So might just do this off to the side. I'm just using Pythagorean theorem. So it'll be the root of 45,000 squared plus 25,600 squared. And this is, let's give that a go, plus 25,600 squared. It's a big number, square root it. I'll just go to the nearest whole. So we use Pythagorean theorem, 51,722 kilogram meters per second. And I should say here too, what we've just found so far is just the magnitude. We still haven't found the angle, but we can do that right now. So let's determine the angle. So this is just, we'll just use tan. And so we're going to determine, let's determine this angle here. So this is the angle east of north. And we're just going to use tan. I'll just show my work to the side. So theta is tan inverse 45,000 over 25,600. See what we get. I got pretty near 60 degrees. So the angle, about 60 degrees. And we basically solved the problem here. To find the speed, I'm going to call this VF after the collision. Remember, guys, momentum is just speed, mass times speed. So speed is just momentum divided by mass. So we're going to take that total momentum that we found and divide by the coupled masses of the car. I might just say M1 plus M2, right? Because those are now combined together. And we got 51,722. The combined masses of the cars, just double check what the cars are, 3,800, so 3,800. So that combined 3,800 kilogram mass, both cars, is moving with a momentum of 51,722. So we'll do that division. And we get 13.6 meters per second. So What speed are the coupled cars traveling at? 13.6 meters per second. What's the direction? Same direction as the momentum, 60 degrees. Remember, guys, momentum is mass times velocity. So momentum and velocity will share the same direction. So one approach to solving a 2D collision problem. Here we knew all of the initial information. So we found the total momentum in the x direction, the total momentum in the y direction from before the collision. We knew that meant that's the momentums after the collision. We combine those together to get the total momentum, at least its magnitude, and the angle that that momentum is in. From there, we found the speed using the momentum's magnitude divided by the mass. So, generally, any problem where you have any inelastic problem where you have two things colliding together, you want to know what their coupled speed is and direction afterwards, can set up in a similar way. Let's look at a second problem, and maybe just a slightly different way to approach a problem. So here, in this case, we have two, you can maybe even think of it as two like billiard balls or something on a pool table. So we have a 1 kilogram mass moving to the right, and it's going to make a glancing collision with mass 2, and mass 2 is at rest. So if you can imagine with a glancing collision, the top mass is going to glance off at one angle, and then the second ball is going to go down at a different angle. And we would like to know, well, if the top mass gets deflected at 3 meters per second at an angle 30 degrees from the horizontal, what angle and speed does the second mass get deflected at? So we're going to approach this in a relatively same manner. We're going to look at momentum in the x direction, the y direction, understand that both are conserved, and use that to answer our problem. So let's see how I've scaffolded this one for us. So remember, momentum's a vector. So momentum is conserved to the x direction and the y direction. So let's talk about what's the total x component of momentum before the collision. Well, before the collision, mass 2 is at rest, and mass 1 is moving to the right, and I'll call that positive. Maybe I'll call up positive 2. All the x momentum is from mass 1, and momentum is just the speed, mass times the speed. So that's actually pretty easy to calculate. So pxi, just 1 times 5 meters per second, 5 kilogram meters per second. And if you want to throw into the right, you can, but we understand that's implied. I chose the right to be positive. What about the y direction? Well, mass 2 is at rest. Mass 1 is purely moving to the right. So there is no momentum in the y direction initially. And here it's just 0. This is an important idea. So because that total momentum initially is 0, when the first ball glances up and the second one glances down, that means that these momentums in the y direction are going to have to be equal to each other in order for the total momentum to be 0. So we're going to keep that in mind as we move forward. So the x and y components after the collision, and again, this isn't a trick, it's just, we want to understand that, hey, momentum in the x direction is conserved. It's the same total momentum, 5 kilogram meters per second. And the y momentum, 0 kilogram meters per second. And that is to the right, according to our diagram. Just make use of that. So we know the total momentum in both directions. After the collision, we only have information about mass 1. We know it's traveling at 3 meters per second, 30 degrees above horizontal. But that means that we can find its horizontal momentum. And whatever its horizontal momentum is, we'll know that the total has to add to 5. So for example, if the horizontal momentum for mass 1 is, say, 3 kilogram meters per second, well, then we know mass 2 is 2 because it has to add to 5, right? So let's find the momentum for mass 1 in the x and y direction. So I've called that P1 XF. In practice, you can use whatever labels you find helpful to you. So what do we have? We have its mass, which is not changing. We have its, I think its mass is 1, right? Yeah. Its speed is 3 meters per second, but now it's at an angle to the horizontal. And the angle we have with the horizontal is 30 degrees. So it'll be cosine 30. And the momentum in the y direction will be 1 times 3 times sine 30. And here, what we're really just using is the fact that the momentum in the x direction will just be the total momentum times cos theta, and the momentum in the y direction will be the momentum times sine theta. Right? If we have some momentum at some angle to the horizontal, we'll have some x component of momentum, some y component of momentum. So we're just using some right angle triangle trigonometry here. So 3 cos 30, that's about 2.6. And for the y direction, 3 sine 30, I think that should just be 1.5. And this is to the right, and this is up. So guys, we can just use some mental math right now. If the first ball has a momentum of 1.5 kilogram meters per second up, and the total y momentum is 0, well, now we know the y momentum for the second mass. It has to match that perfectly, 1.5 kilogram meters per second down. And if the total momentum is 5 kilogram meters per second to the right, and this guy's momentum is 2.6, well, that leaves 2.4 for the x component of momentum for our second guy. So let's use that fact and calculate this. So P2xf, the final momentum for mass 2, that's just going to be the total momentum, Pxf, minus the momentum of the first guy in the x direction. That's just 5 minus 2.4. It's going to be 2.6 kilogram meters per second. And again, that's to the right. For P2yf, that will be Pyf minus P1yf. So remember, that's 0 minus, and we chose up to be positive, so minus, well, it was 1.5, and that gives us negative 1.5 kilogram meters per second. And that is negative 1.5 in the upward direction. So we know this also means that's 1.5 kilogram meters per second down. Now, we showed work for that, but hopefully for you, it's just intuitive. If the momentum for the first guy was up and the total momentum was 0, the other guy has to balance it perfectly going down. Well, now it's a lot like the previous question. Now for mass 2, we have these individual momentums, x and y. We can combine them together, get an angle, and get a speed. So that's what we're going to do. We're going to find the angle and find the speeds. Now, actually, we're going to do this one in a slightly different way according to the walkthrough I've made up. We're going to find the actual horizontal component of speed. And so instead of drawing a vector diagram with the momentums, so P2xf, P2yf that way, we're actually going to scale those down by the masses and draw, so it's going to be the exact same shape of triangle, but we're just going to divide by the mass and just find the final speed that way. So just a tiny bit of a different change in approach to this question. So V2xf, we take P2xf, which was 2.6 kilogram meters per second to the right. And mass 2, I think was it also 1 kilogram? No, it was 2 kilograms. Divided by 2, that's 1.3 meters per second to the right. So that's its horizontal component of speed. Its vertical component of speed will be 1.5 kilogram meters per second down, divided by its mass, 0.75 meters per second, and that's down. And so now we'll use our trigonometry. I'll just draw this a bit bigger. So we have 1.3 meters per second right, 0.75 meters per second down. And we're finding this final velocity. So we'll need the magnitude and the angle. So the magnitude, that's just the magnitude of that velocity vector. We're just doing the root of 1.3 squared plus 0.75 squared. We'll get a value. And then for the angle, we're just doing inverse tan of the opposite 0.75 over 1.3. And we know this will be below horizontal. So let's just finish it off. So about 1.5 meters per second is the speed that mass 2 will fly away, deflect away at downwards. And the angle, 0.75 divided by 1.3, shift tan, looks like 30 degrees. All right, so we know that that second mass, if I can make a small concluding statement, maybe right here, V2F is 1.5 meters per second, and it's 30 degrees below the horizontal. So did I do 1.2, 2 point, did I make a small mistake here? P2, I did. So if you were kind of yelling at your screen, it's one of those. So the x momentum for mass 1 is 2.6, which means when you subtract those guys, it should be 2.4. So I got slightly different answers from when I did this earlier. Okay, so that's 2.4 instead, which makes that 1.2. That's fine. So that's 1.2. So that's just going to change these a little bit, I think. So hopefully when you were doing yours, you just use the correct values. But if you were just copying down what I did, we're off by just a little bit. But it's fine. It's a pretty easy fix. So we just get 1.4 instead. No big deal. And the angle will probably change just a little bit too. 1.2, shift tan. Yeah, 32 degrees. So it's 32 degrees below horizontal, and it's 1.4 meters per second. The same strategy applies, just a small mistake there. So sorry about that. So two walkthroughs, arguably very similar. We think about what the momentum in the x direction is in total between the two objects. We know that's conserved. And then we use vectors afterwards to kind of recombine. In the previous walkthrough, we actually combined the components of momentum in a diagram and found the angle that way, and then found the speed afterwards. In this one, we found the components of speed first, and then found the angle and final speed. Both methods would give you the exact same result. So it's kind of providing with some options. So we're gonna do one more where we don't exactly have a walkthrough. We're just gonna, and if you want to just try this one on your own, like that'd be fantastic. But if you want to kind of go through it with me, let's get one more example in the books, just a bit more practice analyzing 2D collisions. So this is actually a very similar question to the one we had earlier in our walkthrough number 1. So we have a car with a certain mass, with a certain speed, a truck with a certain mass and a certain speed. But this time, the speed is not north, it's north and east. So it's a little bit more of a complicated question. Before, we had the collision looking like this. So it was pretty easy to analyze. In this question, it's east, and then the second guy is kind of going like that. So a little bit more work, but it's not too bad. So we're gonna do this problem using two methods. Again, just giving you guys different tools, and you can kind of choose whichever tool that you like the best. Now, how much I gave myself I gave myself 2 slides for this, so I think we're going to be good. All right, so here's how we're going to go at this one. We're going to use components. So these two trucks are going to, these two cars are going to collide together. So actually, maybe we can get a little visual of what's going to happen. Let's get it on So you can draw this where you have room, but since I have space on this slide, I'm just going to draw it in here. So we have a car traveling that way, and we have a truck traveling that way. Can I draw a truck? There we go. And what's going to happen is they're going to collide, and everybody here can probably reason out which direction the entangled car and truck will go afterwards. They're going to move right, and because there's some upwards momentum from the truck, they're going to move up and right, something like this. They're going to be all coupled together, moving up and right, and their combined mass together at that point will be 3,200 kilograms. But we want to find what that final speed is, right? We want to know what that angle is, right? So that's the idea of the question. So given all this stuff, here's what we're trying to find. So the way I'm going to frame it is I'm going to frame the problem this way. So 1, momentum is conserved in the x direction. So what does that look like? Because both objects have momentum, right? So we have mass 1, v1, x plus mass 2, v2x. So this is the x component of momentum for the car initially and the truck initially. And afterwards, we have I'm just going to write m for their combined masses just to save myself some work. Equals m times vf, like that. So if you think about what I'm doing here, guys, it's nothing different than the walkthroughs. Finding the total momentum in the x direction. That's going to be equal to the momentum in the y direction. And I should say VFX, actually. That's going to equal the total momentum afterwards in the x direction. And I know everything here. I know the masses. I know their initial speeds. So I can actually find the final speed in the x direction pretty quickly and efficiently. So VFX, it's going to be, and you know what? Maybe let's, in this particular problem, because we have so many indices floating around, let's just actually plug in. I think that'll be more helpful for us for this question. So mass 1, so 1,200. And mass 1 is just moving perfectly to the east, so 18. For mass 2, though, it's moving at 25. Its mass is 2,000. Speed is 25, but we have to find that x component, right? So maybe off to the side here. We know that it's traveling at 25 meters per second. And the question says that it's traveling at an angle of north 20 degrees east. So that's like that, right? So if we're thinking about whether to use sine or cosine, here this angle is the angle with north and v1x is the opposite. So we'll be doing the sine of 20 or the cosine of 70, whatever you prefer. I'll do sine 20 equals combined mass 3,200 times VFX. So let's figure this out, guys. 1,200 times 18 plus 2,000 times 25 times sine 20. So about 38,701. And now we can just solve for VF. Divided by 3,200, about 12.1 meters per second. And we know from our setup, we know in the x direction, this should be x. We know in the x direction, that's going to be right. I mean, it's just obvious from the context of the problem, right? So we're going to do the same thing for the y direction. Momentum is conserved. in the y direction. That is an ugly conserved, but you guys will live. So m1 v1y plus m2 v2y equals the combined mass times vfy. Momentum is conserved in the y direction. But guys, our mass 1, the car, is traveling purely east. So momentum in the y direction is 0. And this one's pretty easy to find vfy by itself. So I'm just going to solve for it. m2 v2y divided by m. So that is mass 2 is 2,000. v2y is 25 times the cosine of 20. And the total mass, 3,200. So we'll have our v2y now. 2,000 times 25 cos 20 divided by 3,200. So I got about 14.7 meters per second. And we know that's north. Do I have room to come? I think I have room just to finish the problem on this slide. I think I will. So let's set this up. Let's finish this off here. So we know our final speed is going to be in this direction, VF. We know the components. We found them out by analyzing conservation momentum in each direction. So we have 12.1 meters per second to the right, 14.7 meters per second up to the north, and east. And so let's just find that angle, find that result. So I think hopefully at this point, you guys are just really comfortable applying Pythagorean theorem and inverse tan. So I'm going to just, shave off a step here just because my screen is getting kind of filled up. And I'm just going to crank it out. If you want to show an intermediate step, so it helps you coming back and studying this, you can. That final speed using Pythagorean theorem is just 19 meters per second. And the angle using inverse tan, 12.1 divided by 14.7, about 39 degrees. So the final speed of the coupled car and light truck, 19 meters per second. And our angle is 39 degrees. This is the angle from our diagram. This is the angle east of north. So 39 degrees east of north. And we've got it. So we've analyzed another collision. Now, I'm going to argue the process we used here is exactly the process we used in walkthrough 2. We set up an equation equating momentums before and after, and we found the velocities by dividing by the total mass. It's just it's not scaffolded, and in practice things won't be scaffolded for you. But hopefully now we have this example, you kind of see how that process works. So I was using components. The other way we could do this is by using trigonometry. So by drawing a triangle of momentums. So let's do that, and we'll be done this lesson. So the total momentum for the whole system is the momentum of the car, call it mass 1, plus the momentum of the truck. Well, let me find these momentums and then draw them out. So momentum of the car, that one's easy because the car's mass is 1,200. Well, they're both easy actually. And its speed is 18 meters per second. So its total momentum is 1,200 times 18, 21,600 kilogram meters per second. And we know the direction. The velocity is east, the momentum will be east too. Let's calculate the momentum of the light truck. So its mass is 2,000, traveling at 25 meters per second. That's 50,000 kilogram meters per second. And I know its direction too. So that's 20 degrees east of north. Let me draw that vector addition, P1 plus P2, for those momentums. It would look something like this. So you'd have P1 going east, 21,600, P2, try to draw it a little up to scale here, 50,000. And our total momentum would be something like so, PT. And finding an angle in this question is actually pretty easy, because the angle between east and north, this dashed line, is 90. And our question tells us that this angle is 20 degrees east of north. So that means the entire angle here is 110 degrees. So in my opinion, for a problem like this, using vector addition and trigonometry, in my opinion, is actually a lot easier, because we can use the cosine law to quickly find momentum and then divide by mass to get speed. And we can use the sine law to get the angle like really quick. So let's do it. So the size of that total momentum, set up my cosine law. So 21,600 squared plus 50,000 squared minus 2 times 21,600 times 50,000 times the cosine of the angle between them, which is 110 degrees. Let's crank that out. Now, hopefully we get the same result for the speed here. So it's nice doing it both ways, because we can kind of check our answer. Squared 2 times 21,600 times 50,000 times the cosine of 110. It's good for me too, because I don't have a class all in front of me to like make, point out if I've done something wrong. So I've got about 60,871 kilogram meters per second. And so I know that the final speed, whatever that is going to be 60,871 divided by their combined masses, which is 3,200. Cross our fingers. So 19 meters per second, which I believe is, it's what we got before. I'm expecting to get the same angle as well. So let's give that a go. So now that's sine of theta over 50,000 equals the sine of 110 over that side we just found. And that's the momentum, right? So 60,871. So sine theta equals, so we will do 50,000 times the sine of 110 divided by 60,871. About 7719. And so theta equals 51 degrees to the nearest degree. And before you panic and say, we didn't get 51 degrees before. No, because before we found the angle east of north, here we're finding the angle that's north of east, right? And so our final VF is 19 meters per second, and the angle is 51 degrees, but this is north of east, which is the same as 39 degrees east of north. So in my opinion, for a problem like this, having a walkthrough with all the momentums being considered in the X and Y direction is great. But if you can draw a diagram showing the total momentum, because we know that the total momentum is the same before and after the collision. So by finding the total momentum before the collision, we can just go right to analyzing what the speed and angle is afterwards. And for this problem where the car and truck were just moving with one speed afterwards, I think the trigonometry method is really applicable, really useful. So we've done 3 examples, a variety of approaches. They're all very similar, so you can kind of pick and choose what kind of helps you. But the key is that momentum is conserved in the X direction and the Y direction, so we can approach 2D collisions by looking at components. So what's next for you guys? I have a little assessment where you're going to reconstruct a simple car crash. So I'm going to tell you guys, this will be our starting point. I'm going to say 2 cars, one traveling north, one traveling east, had some kind of final velocity when they coupled together and crashed together. And I'm going to have you guys work backwards to find their initial speeds. So you're being forensic scientists analyzing a collision, trying to see what happened before a collision. So that should be pretty fun. And this lesson actually does kind of wrap up our Unit 3 on energy and momentum. So what we'll be doing next is we'll be looking at what I call field theory. So we'll revisit gravitational fields, talk about what a field is, compare that with electric fields. We're going to see a whole bunch of comparisons, things in common between gravitational forces and fields. We're going to update our knowledge of gravitational potential energy, and then look at the parallel to electric potential energy and electric potential. And then finally, we'll look at connections between electric fields and magnetic fields. So I just like to lump all this in and call this field theory. We do a lot in this next unit, a whole bunch of cool, interesting things. I can hardly contain my excitement, guys. But that will be for another lesson. For now, we've wrapped up this unit. You have the car crash reconstruction tasks to do and review to start working on. All right. Hope you guys are staying well. Have a great day, and we'll see you soon.